All right, so we're finding the derivative today of an inverse trigonometric function. And so as you take a look at this particular equation, we know it's the inverse trigonometric because remember that power of -1 means inverse. It doesn't mean we actually are like doing 1 over sine. It's the inverse specifically. All right, so in order to do this, we don't currently have any rules for being able to find the derivative of an inverse sine function. But we can actually manipulate it and use some of the work that we were doing last week in order to be able to help us. We can rewrite this equation as sine of y equals x. Basically what we're doing is we're taking sine of both sides of the equation. Because inverse sine and sine cancel each other out. Now, technically speaking, this is actually only going to be true technically for y values between -pi/2 and pi/2. Because there's the whole cycling thing, but we're still going to be able to get the right answer this way. And we're still going to be able to derive it this way. So it's okay. All right, now that I wrote it like this, sine of y equals x, we can use implicit differentiation to find the derivative of this function. All right, so when doing this derivative now, remember that when we do the derivative of sine y, that's going to be able to give us, or that's going to require chain rule, and so it's going to cosine of y times y prime. Well, we're making progress. We want to figure out what y prime equals here. So I can go ahead and divide both sides by cosine of y.
Y prime.
So we're now looking at this. Y prime equals 1 over cosine of y, which, yes, would also equal secant of y. But I'm actually not going to go secant here.
Wait.
All right. So if I'm not going to turn into secant of y, I need to be able to do something else because I don't want my derivative every single time to be in terms of y, so I'm going to do a little bit of manipulation. We're actually going to do something a little bit tricky that you might not have seen coming.
No. Leon, can you please
Take a look at this and write it down and then figure out why can we do this. So, have you figured out why that actually equals cosine?
No.
Well, if you're not sure, remember this. Sine squared of x plus cosine squared of x equals 1, right? Well, what would you get if you solved that equation for cosine? Well, you'd have to subtract sine from both sides, sine squared from both sides, right? And then you'd have to take the square root of that.
Why? Why the square root?
And so cosine squared equals 1 minus sine squared. And so if I want to know what cosine is, I then am taking the square root of both sides of the equation. All right, so, and by the way, you'll notice I chose to write it as sine of y squared. Of course, that does mean the same thing as sine squared of y. I just wrote it this way because it's a little bit easier to look at, a little bit easier to read. Having gotten to this point, of course, the question you're probably asking is, why on earth is this an improvement? Why would we want to do that? Well, it actually goes back to that second line. Remember that we know that sine of y equals x?
Oh, God. Oh, the x squared.
Which means we can get rid of the y here because I created a situation that has sine of y in there instead of cosine of y. And by doing that, we can get rid of sine of y and just have it all in terms of x. And so the derivative of inverse sine is actually 1 over the square root of 1 minus x squared. Yes, we could rationalize it, but I'm not going to make it. It's easier to remember in this form. And in fact, remembering it's going to be a deal here because this is going to be one of the rules that we're going to have to know going forward. In fact, there's a whole bunch of rules with these, right? We could use this exact same method to find out what the derivative is of inverse cosine, inverse tangent, inverse secant, inverse cosecant, and of course inverse cotangent. But rather than going through the work for every one of those, I'll go ahead and give those rules to you to put onto your derivative rules sheet in your notes. So we're now going to find the derivative of an inverse sine equation. Notice it's not just inverse sine of x, it's inverse sine of 3x. So Chain rule. Since we have a function within the function, we're going to have to use chain rule on that part. So, to find our derivative, we start with just the general rule for the inverse sine. So that's 1 over the square root of 1 minus, but it's not going to be x squared. It has to be whatever was inside. So it's going to be that 3x there. So it's going to be 1 minus 3x squared. Now that's the derivative of the outer function, the derivative of the inverse sine. I still got to multiply that by the derivative of the inner function, which is the derivative of 3x. So yeah, that's just 3.
That's not so bad.
Now, looking at it, this isn't necessarily all that cleaned up. We can clean it up just a little bit, and yes, I'd like you to do this. At least put that 3 into the top of the fraction there. And down below, you can either leave that as the quantity of 3x squared, or you could turn it into 9x squared. Either way would be fine there. All right, so for this one, you worked it through on your own first, but then let's take a look and see what we should get here. Now, notice again, it's going to be a chain rule situation, but in this case, we're actually going to have to use chain rule a couple times, as you'll see. First step, I'm going to deal with the outer function. Derivative of the outer function, that's the derivative of inverse tangent. That is 1 over 1 plus x squared. But it's not going to be x squared. It's going to be whatever was inside. That's the inner function. So it's going to be e to the 2x. Right, now, I need to now multiply it by the derivative of e to the 2x. Notice in order to find the derivative of e to the 2x, that's using chain rule as well. So that's going to be e to the power of 2x for the outer function, times the derivative of the inner function. That's 2x there, so derivative of 2x is just 2. So it's going to look like that.
That's what I was thinking.
Now, go ahead and clean it up a little bit. So y prime is going to equal 2 e to the 2x over 1 plus, and again, you can leave it as e to the 2x squared, or even better, e to the 4x. Because remember, when you do a power to a power, you multiply the exponents. So I'm multiplying the 2x by the power of 2. All right, now first of all, when you see arc secant, remember arc secant is just another way of noting the inverse of secant. So this would be the exact same thing as writing it this way.
Why would you do that to us?
You gotta be able to see it both ways and understand what both of them mean. It'd be a shame to do all this work and learning how to do derivatives of these things, and then just because they wrote it a different way to not have any idea how to handle it. So the first step that you go through is you start plugging the stuff into the derivative for inverse secant. So you look back at your notes, put the stuff in, and so you notice x squared is now in the place of x in both cases. The one that's kind of tricky for us to see at times here is this one. Because we write x squared, and then it's really tempting to say, hey, I used the squared. So pay attention to that and make sure you did the x squared squared. But now this line is not yet totally done though. Because remember, we have to be using chain rule. So I still have to multiply it by the derivative of x squared, which of course is going to be 2x. Now if I have it like this, then clean it up. And when you clean it up, you should end up with 2 over x root x to the 4th minus 1.
Wouldn't it be x squared?
Now some of you might be thinking though,
you canceled out the x's.
what about the x squared? Where'd that x go? Well, notice if I put an x in the top here, actually let's do a different color here, and I have the x squared on bottom, I can cancel those out. And so we want to reduce and simplify anywhere we can, so we go ahead and we do that part in terms of the simplification. And then, yes, this is done, this is your final answer.
I really like how
Now, having done these, pretty soon you are going to need to actually have those inverse trigonometric derivatives memorized. As you take a look at the rules, these are the same ones that you wrote down earlier. What are some patterns that you see here that are going to help you to memorize this thing.
CSC and
Yeah, you'll notice
look the same.
that we have certain pairs here that are common pairs.
And sin and cos.
Sine and cosine. Cosecant and secant. And
Saving prior line.
tangent and cotangent.
Yeah, it's a really heartwarming drum.
You notice that with all three of those, that the derivatives are exactly the same. The only difference is that one is the opposite of the other. So one's positive and one is negative. They're otherwise exactly the same, which means already you're down to like memorizing just half of them, if you can keep it straight about which one's positive and which one's negative. Yeah, notice which ones are negative up here. All of the cos are negative. So cosine gives us a negative. Cosecant gives us a negative. Cotangent gives you a negative. So already you don't have to memorize all that much. It's just helping to get us down there.